Good morning. It's a great honor and pleasure to be here today. It's an honor because the Abel Prize is one of the big days of the mathematical calendar. And it's a pleasure because it so happens that I know Endre Szemerédi very well. I work in a similar area and I've known him for many years. That's not why I was chosen to be here. I was chosen before the decision was made. So it was a delightful surprise to learn that he was going to be the winner. Although in some ways it's not a surprise, as I hope to convince you, because he really is one of the world's great mathematicians, and so it's a very, very fitting honor for him to receive the Abel Prize. As we've just heard, the area that he works in is combinatorics, and although that's not, he also has worked particularly in the subfield known as extremal combinatorics, although not exclusively in extremal combinatorics. And well, different mathematicians are famous for different reasons. Some mathematicians are famous for one or two very, very major theorems that they've proved. Some are famous for a huge body of work that has profoundly influenced a field. Szemerédi is one of the rare examples that fits into both categories. So we've just heard that he has Szemerédi's theorem, Szemerédis regularity lemma, and a few other results famous results that bear his name. But he's published over 200 papers with many top quality results contained in them. I cannot hope to show you more than a tiny part of what he's done, but it should be borne in mind that what I'm going to say is just a very small sample. Let me just say a little bit more about what combinatorics is. I'm going to give various properties that typical results in combinatorics have, although for each one it is possible to think of exceptions. So each thing I say is a characteristic feature of combinatorics. There are some parts of combinatorics that don't have those features, but taken together, I think these features do give some idea of what combinatorics is like. So broadly speaking, combinatorics deals with mathematical objects and structures that can be specified in a finite way. Combinatorics is more to do with the finite than the infinite, although I should say that there is such a thing as infinitary combinatorics. It tends to be about the discrete rather than the continuous. So a discrete structure is, so to speak, something where to get from one part to another, you have to jump. If I talk about the words in the English language or the Norwegian language, if you want to change from one word to another, you can't smoothly change the word from one to another. You have to change a letter in a jump. You may have to change several letters. If I want to talk about something like positions that a human body can be in, that's more of a continuous structure. As I move my hands around, they don't jump like this, they can move smoothly. So if I wanted to study the set of all possible positions of the human body, that would be a continuous problem rather than a discrete problem. Usually, at least in the part of combinatorics that Szemerédi has been most active in, you don't make very strong structural assumptions. So the objects, if you want to come up with an example of the kind of object that Szemerédi would mostly study, it's very easy. Whereas there are some parts of mathematics where even producing an example of the objects that are studied is difficult, and what happens here has a big effect over what happens here. That's not so much the case in combinatorics. A very appealing, for some people, including me, very appealing aspect of the subject is that a lot of the problems are extremely easy to state. So that the questions are so easy to understand that you feel they must be easy to answer, but often that turns out to be very far from the case. And so there's something about it that almost forces you to think about the problems. And as we've already heard, there are very close connections between combinatorics and computer science. So here is a combinatorial structure that is one of the central objects of study, the graph. What is a graph? It's a collection of points known as vertices, and some pairs of vertices are joined by lines, or as they're known, edges, and some are not. So here, if we think of these points as being numbered as on a clock face, there are 12 of them, you can see that the point that's at 1 o'clock is not joined to the point at 2 o'clock, but it is joined to the point at 7 o'clock and 8 o'clock and so on. This may look like a continuous structure because you can move continuously along the edges, but it's not, because all we actually care about with a graph is just the data of which points are joined to which. We don't really need this picture at all. We could just have a list that says things like point number 2 is joined to point number 9, and so forth. So it's a discrete structure. Another way of seeing that is to say, if I want to change this graph into another graph, I can't smoothly vary it so that it becomes the other graph. I just have to remove an edge suddenly or add an edge suddenly. Now this picture gives a little bit of a misleading idea of what combinatorics is like, because it's rather simple. There's only 12 points, and you could imagine that if you looked at it for long enough, you could say everything you wanted to say. But perhaps that feeling you won't have quite so strongly if I show you a more complicated graph. This one was produced by somebody who wanted to model the internet. So here, the vertices represented websites, and the edges represented links between websites. And this is a very important point to make about graphs. They can be used to model a lot of things. There are many situations where you have a set of objects and you have some connections between them and some that are not connected. What about extremal combinatorics? I think that's best illustrated with an example of a simple-ish, certainly simple to understand, question in extremal combinatorics. So imagine you've got a graph with n vertices, and you want to put in as many edges as you can, but never form a triangle. So a triangle just means you have 3 vertices, and they're all joined to each other, so that if you draw the lines, you'll get something that looks like a triangle. It turns out that the best way of doing this is to take your points, and divide them into 2 sets as equal as you can. So if, let's say, n is even, then you'd have n over 2 points here, n over 2 points here, and you join all the points in this set to all the points in this set. And that's the only edges that you put in. So why does that not have a triangle? Because if you take a point and you follow along an edge, and then you follow along another edge, and then you follow along a third edge, you'll end up in the other set. So you can't get back to where you started, so you can't draw a triangle. And how many edges does that graph have? It has 1 for each pair of 1 point here and 1 point here. So that's n over 2 times n over 2, which makes n squared over 4. It's harder to prove that you can't do better than that. So I've shown you can get n squared over 4. You need to do a serious argument to show that you can't get more than n squared over 4, but you can't. It's a special case of a result known as Turan's theorem. And so why do we call that a question in extremal combinatorics? It's because you're trying to make some quantity, in that case the number of edges, as big as possible before something else is forced to happen, in that case a triangle appearing in your graph. So now let's move on to Szemerédi himself and the famous theorem about arithmetic progressions. And if you want to sum up this theorem as a slogan, perhaps you could say, arithmetic progressions are hard to avoid. What is an arithmetic progression? It's a sequence of numbers that's generated in a particular way. If you look at these numbers here, if you look at them for a second or two, you may spot a pattern, that to get from each number to the next, I'm adding 12. I went from 1123 to 1135, 1147, 1159. Each time I was adding 12. So the jump from each number to the next is the same. And that's what makes it an arithmetic progression. This we would call an arithmetic progression of length 7 and common difference 12. So now let's imagine a game that you might play based on the notion of arithmetic progressions. So imagine you have a very large set of cards numbered from 1 to n. So n is a big number. And what you have to do in this game is pick as many cards as you can. But somebody has told you another number, which I've called k here, but if you don't like letters, then think of k as, say, 5. The only rule that you have to obey is that when you've chosen the cards, it's not possible to find, amongst the cards that you've chosen, some cards that have numbers on them that form an arithmetic progression of length 5. So you have to choose as many cards as you can without making an arithmetic progression of length 5. Or, as I say, you can play the k game, where k is bigger than 5. What does Szemerédi have to say about this? Well, here's a version. I've changed my k from 5 to 23. If you understand this, then you basically understand the theorem. What he can show is that if n is large enough, then even if you pick just 1/10 of 1% of the numbers between 1 and n, there's no way you can avoid, amongst the numbers that you've chosen, there being an arithmetic progression of length 23. Now, the only confusing thing about that is there doesn't seem to be anything very special about the number 23. or about 1/10 of 1%. And if that's your reaction, that's very good. You have good mathematical instincts. You can replace 23 by any other number, and you can replace 1/10 of 1% by 1/1,000,000 of 1% if you want, and the result is still true. But this is just if you can prove this, you can prove the whole theorem. So how does the proof go? I'm sorry, I'm not going to tell you. But I can give you a little bit of a flavor of the proof by showing you a diagram that comes from Szemerédi's original paper. This diagram is intended to illustrate the logical structure of the argument. And I think even that diagram is quite complicated. What's the caption? I don't know whether you'll be able to read it from there. It says, the diagram represents an approximate flowchart for the accompanying proof of Szemerédi's theorem. Actually, why does it say Szemerédi's theorem rather than my theorem? It's because, in fact, Szemerédi explained the proof to two other mathematicians, Ron Graham and Andras Heinal, and they wrote the paper. So they've used Szemerédi in the third person. I don't understand why some of the arrows have dotted lines and some have full lines and so on. I'm sure there is an explanation. So anyway, you get the idea. It's a rather complicated argument. And each of these circles themselves represent something that is itself quite difficult to prove. So another question that might occur to some people is, why should we mind about this result? What is so interesting about the fact that if you choose quite a lot of numbers between 1 and n, you're forced to have an arithmetic progression of length 23? So the first thing to say is this is not going to help us build bridges and things like that. But there are lots of reasons that it is important. So we've already heard about a direct application of Szemerédi's theorem, and Ben Green and Terence Tao proved a famous theorem much more recently that says that you can find arithmetic progressions as long as you like, consisting just of prime numbers. Here's an example of 5 prime numbers that form an arithmetic progression. It turns out that you can get arithmetic progressions of primes as long as you like. And Green and Tao, by means of extremely clever arguments, managed to reduce this problem to a form that could then be deduced from Szemerédi's theorem. So to call it a direct application doesn't mean apply Szemerédi's theorem, you're done. It means do a lot of work and then apply Szemerédi's theorem. And there are other direct applications, but one shouldn't focus solely on those because that's to miss a large part of how mathematics progresses. There are also indirect applications. It's very often the case, especially in combinatorics, that if you have to struggle to solve a hard problem, then you have to invent or you have to understand things that weren't understood before, general ideas in mathematics, and you have to invent new techniques. And once you've done that, it's quite likely that those new techniques and ideas are going to be used in many other contexts, and that was very much the case with Szemerédi's theorem. In particular, as we heard a little earlier, it gave birth to a tool that has become one of the absolutely central tools in extremal combinatorics, known as Szemerédi's regularity lemma. Very roughly what this says is you take any graph, it's best to think of this as quite a big graph, and there is a way of dividing up the vertices of that graph into a fairly small number of sets in such a way that if you look at any two of those sets of vertices and you look at the edges that join those two sets of vertices, what you see looks random. Now, I don't expect you to take in the significance of that straight away, but let me make a few remarks about why this is such an exciting fact. So one thing to say is you might think that looking random is about the worst thing that you could have, because if something looks random, it means surely you can't say anything about it at all. In fact, the exact opposite is the case. If it looks random, it means that it has what you might think of as more statistical properties that actually mean that you can say a lot of things about the graph. A very simple, an example of the sort of thing you can say, if you've got a graph that looks random, you can say how many triangles it is likely to contain, roughly. But many other things like that. So the theory of random graphs is a very large and well understood area of combinatorics. So if something looks random, actually combinatorialists are happy rather than sad. And when I say looks random, you have to come up with some idea of what looks random means. But there is a well understood notion of what you might call pseudo-randomness, that in a sense The understanding wasn't so great when Szemerédi was working, so he actually contributed a lot to our understanding of pseudo-randomness by means of this regularity lemma. So once you know that, once you sort of feel that you understand random graphs, it means that with the help of the regularity lemma, you're dividing your graph into just a small number of sets, and all you really need to know about the edges joining this set to this set is they look pretty random and there are roughly this many of them. So there's not much information that you have to store about your graph before, for many purposes, you really feel that you understand that graph. And this result has had huge numbers of applications, one of which is to the property testing, as was mentioned a little earlier. I'll make one extra remark about property testing. It comes out of a theoretical model due to computer scientist Leslie Valiant for something called machine learning, which is roughly speaking computers learning to make hypotheses based on a small number of observations, which I think is something of sort of clear practical importance. So there is some sort of connection between this seeming puzzle in combinatorics all the way to something that's right at the forefront of artificial intelligence. I haven't got much time, so I'm going to rush on. It was mentioned earlier that there was a sorting network due to Erte, Komlosh, and Szemerédi. One almost thinks of Erte, Komlosh, and Szemerédi as a separate author because there are so many papers with wonderful results due to those three. And one of their really famous ones is their sorting network. So what is sorting? The idea here is you've got n objects that you've got to put in order, and the only thing you're allowed to do is take two of them and compare them. So if you want to visualize this, what you could imagine is you've got 1,000 rocks on a table. They all look roughly the same, but in fact, no two have the same weight. So you want to put them in order of weight. And all you've got is a pair of very accurate scales in front of you, and the scales only fit one rock on this side and one rock on this side. So the only thing you can do is pick up two rocks, put them on the scales and see which one goes up and which one goes down, then you know which is the heavier. And your task is to put them in order of weight using the scales as few times as you can. So how well can you do? The answer is roughly the number of rocks you have times the logarithm of that number. This result is not due to Erte, Komlosh, and Szemerédi. It predates them. It goes back to at least 1945 when John von Neumann came up with a procedure called merge sort, and Szemerédi was only 5 in 1945. The reason you need n log n is a beautiful argument, actually. You have n factorial arrangements to start with, and each time you do a measurement, there's only two possible answers. So the best you can hope to do is divide the number of orderings that's consistent with the questions the answers you've received so far by 2, and the number of times you need to divide n factorial by 2 to get down to 1 turns out to be roughly n times the logarithm of n. But as I say, that result is not due to Erte, Komlosh, and Szemerédi. So what did they do? They did something called parallel sorting. So let's imagine a slightly different situation. This time you've got your 1,000 rocks, but now you've got 500 sets of scales, and you've got an army of 500 assistants. So what you're allowed to do is to tell your various assistants, you take those 2 rocks, 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 go off and measure them all at the same time, and then come back and tell me what the answers were. So each time you do that, let's call that a round of the sorting. And the question now is, how many rounds do you need? And the significance of this is that if you have parallel processors that can do things at the same time, you want to know whether you can make the computation work much more quickly. And the answer is yes. You clearly need at least log n rounds, because in each round you can only do n over 2 comparisons, and you need to do at least n log n comparisons. So there's a very simple argument that says that the number of rounds you need is at least the logarithm of the number of rocks that you start with, or the number of objects you start with. And Erte, Komlosh, and Szemerédi proved in a remarkable paper that this theoretical minimum number of rounds can actually be achieved, at least to within a constant. I can give a very, very brief sketch, not of the whole argument, but of one important part of the argument. So the first thing they do is something like this. You take all your rocks, and you put half of them over here, half of them over here, not having done any comparisons at all. So you know nothing about whether these are heavy or these are light and so on. And then you just pair your rocks with each other in a random way. So each one here you pair off with one over here. If this one is heavier than this one, you leave it where it is. If it's lighter, you swap them over. So you're trying to put the light rocks on this table and the heavy rocks on this table. Now, if you just do that once, some of the ones that were lighter will have moved to the lighter table, but there's no reason to suppose that they all will. But then you just randomly repeat this procedure. And if you keep on randomly repeating it, say 100 times, then even then you won't necessarily have moved all the rocks that are in, say, the lighter half of rocks to the light table and all the heavier ones to the heavy table, but you can show that you will have moved most of the lighter ones to the light table and most of the heavier ones to the heavy table. And it turns out that you don't have to do this purely randomly, you can also do it pseudo-randomly in a sense, so you don't need randomness for this algorithm. If you could get all the heavier half on this table and all the lighter half on this table, you could just then repeat the process in parallel on this table and on this table and keep going. Unfortunately, it's most rather than all, so you have to work quite a lot harder. But nevertheless, they managed to carry out an argument based on this general scheme. And I think I've got time for just one more result to describe very briefly. About the Ramsey number R3k. So this is addressing the following question. How many vertices can a graph have without, so two things that you're trying to avoid now. One is you're trying to avoid a triangle, but the other is you're not trying to avoid what's called an independent set of size k. An independent set means k vertices, no two of which are joined. So if you wanted to avoid triangles, you could just put no edges in at all, but then you'd get lots of large independent sets. So you want to avoid both triangles and independent sets. How many vertices can it have? And the largest number is called R3k. Here's a quick argument to show that you can't get k squared vertices. So if you haven't got a triangle or an independent set of size k, then no vertex can have k neighbors in the graph, because no two of those neighbors are allowed to be joined to each other, or you'd get a triangle. If this vertex is joined to that vertex, and they're joined to each other, you get a triangle. So if a vertex has k neighbors, no two of those neighbors are joined, and then you've got an independent set of size k. And that allows you to do the following procedure. You pick a vertex, it has at most k neighbors, throw those neighbors away, but keep the vertex. Now take another vertex, which won't be joined to this anymore because you've thrown away all its neighbors, put it over here, take its neighbors, throw those away. Now the most k minus 1 vertices that you've thrown away, you just keep on picking vertices, throwing away their neighbors. And if you've got k squared vertices, then there's no problem in doing that process k times, and then you've got k vertices that aren't joined to each other, and that gives you an independent set of size k. So that just gives you, I don't know whether everybody will follow that argument, but anyway, by the standards of research mathematics, it's a reasonably simple argument. And Erte, and Szemerédi showed that you can improve on this easy argument by a factor of the logarithm of k. It very often happens, including here, that there's an easy argument, and then it's extraordinarily hard to do any better than the easy argument. What they did was they thought to themselves, wouldn't it be nice if there weren't so many edges around? The fewer edges there are, the easier it's going to be to pick a vertex with not too many neighbors, and that way when you throw away the neighbors, you're not throwing away so many vertices, so perhaps you can keep the process going on for longer. And they found a very clever way of making sure that when you throw away a vertex and its neighbors, you also throw away quite a lot of edges, so that the total number of edges in the graph that remains goes down in such a way that you can prolong the procedure by a factor of log k. That actually wasn't their first argument. Their first argument was a more difficult argument, but an argument of great importance because it introduced semi-random methods that were mentioned earlier, about which all I will say is it's another very, very useful technique in extremal combinatorics. And one other thing to say about this is that 15 years later, Korean mathematician Yong-Han Kim proved that you cannot do better than k squared over log k. So that also shows how impressive the result of Erte, and Szemerédi was. It was the best possible result.